Okay, for the last section, we're going to take a look at lines and planes in space. Okay, so in 3 dimensions. For this, well, the thing about describing a line, when we describe a line in 2 space, you have a slope and you have its y-intercept. Okay, the slope is essentially giving you direction, whereas the y-intercept is giving you position. Well, when we do this for vectors, you actually end up using something like the y-intercept, but instead of being the y-intercept, they more do things in that point-slope form, where it could be any point anywhere. So rather than slope-intercept form, it's more similar to point-slope form. So if you have some point out here that the line is going through, the direction is going to be determined by a vector. So you're going to have a vector that's at the origin that shows you the direction the line's traveling, and then you're going to have some point on that line that the line passes through. So the idea is you're going to be parallel to this vector down here, passing through this point. That's the way they describe the line. Okay? Visually, what this ends up looking like is you have that direction vector, and then you have those numbers for whatever that is, A, B, C. Then you have some point out there somewhere. It doesn't honestly matter what point you're using as long as it's on the line. Well, because to find each one of those values from P to Q, you could just subtract some x out there somewhere, minus each x value of the initial point, and then keep doing that. Well, that's going to be the same as some scalar multiplier applied to that vector in vector form. So what that lets you do is actually write these equations in 2 different ways. You can write them in parametric form, which is why we went back and looked at 10.6, where you have some arbitrary value, some parameter t, that your x value, your y value, and your z value are all based off of. So when t equals 0, you're going to get a certain x, y, z. When t equals 1, you're going to get a different x, y, z. So those are points in space, and you end up forming a line from those points. That's a parametric equation. You can also have what's called a symmetric equation, which is what t is equal to in each case. Well, if t is equal to the same thing each time, well, then each one of these you're just solving for t. That means all 3 of those fractions would have to be equal. So you need to be able to write both a parametric solution, or equation, and a symmetric equation. But they all come down to the vector ABC and the point XYZ, and plugging those in. Okay, so actually, mathematically, it's not too bad at all. If I want to find the parametric equations for this line, stop doing that. There we go. That goes through the point 3, 2, 1, parallel to negative 1, 3, 5. So what's your ABC here? Yeah, the negative 1, 3, 5 here, that's your A, B, and C. Those are the multipliers. That's like your slope. Just like M you multiply times the x, you're going to multiply these times that x value. And then 3, 2, 1 are going to be your x1, y1, and z1. So if I want the equation for x, I'm just going to take the x1 value and then add to it this negative times the t, or 3 minus t. What would your y value look like? 2 plus 3t. What about your z value? 1 plus 5t. There's your parametric equations. Then for symmetric, I just want to solve for t. So what would be the x part of the symmetric equation? Say that one more time. 3 minus 1 over x? Remember, you're solving for t, right? Yeah, you could either do 3 minus x, or just to keep it in that fraction format, you could also move over the 3. So you have x minus 3, and then what are you dividing by? Negative 1. I'll keep it in that format. Honestly, if you have this, that's fine as well. Or if you have negative x plus 3. Any of those 3 would work. The other ones are a little more obvious. What's it going to be for the y? Y minus 2 over 3. And for z? Z minus 1 over 5. So these are your symmetric equations. These are your parametric. Yeah.
Are we gonna have like 10, 6 problems on the test, or are they just, can we just do that?
You might have like 1 or 2. Yeah. But mainly it's going to be the stuff from section 4 that uses the parametric stuff. Not too bad though for this? Okay. What about this one? Same question. Except they're just giving you 2 points on the line. Say that again? Yeah, turn it into a component vector, that starts the origin, right? So in other words, if I label this as P, this is Q, then I'm looking for the vector P to Q, which would be what? 3 negative 3, 3? Okay. So, then what? This will be the ABC. Does it matter which one I actually use? No. Does not matter which one you use. So if we just use the initial point P there, so I'm going to use that as X, Y, Z. So then the parametric is going to be X equals what? 1 plus 3T for the Y. What is it again? 3 minus 3T. There we go. Z? Negative 2 plus 3T. Okay? So then, that's the parametric. That's my first part of my answer. For the symmetric, what are you going to have? For your first fraction. X minus 1 over 3, then? Divided by negative 3. And? Over 3. There's your equations. Pretty simple? Because this is negative 2 here, so you're adding 2. We're just taking each one of these 3 and then solving for T. So then the idea is if I plug these values in, I should get the same fraction. So if I plug in 4 here, I'm going to get 1. If I plug in 0 here, I'm going to get 1. If I plug in 1 here, I'm going to get 1. If I plug in the 1, you're going to get whatever, you'll get the same fraction. Okay? Now, when you talk about planes, now the problem with planes is if you have 2 intersecting surfaces, or sorry, if you have a flat surface, right? I need to be able to describe the entirety of that surface. Well, it's not just along a single line, though. It's a bunch of points, right? Infinite numbers spread out in all directions along that plane. But I need to somehow describe them all. So what they do is they end up cheating it a little bit. Rather than to describe the plane, they actually describe what's called the normal vector to it. Normal is just another way to say orthogonal or perpendicular. Okay, so if I look at a flat surface, I just look at this paper, I don't want to actually generate an equation to describe this whole sheet. So instead what I do is I describe this vector coming out of it. If I have that vector coming out of it, and I know where it stops, where it intersects that plane at, that's enough to actually be able to describe the entire plane. Because if I change this angle, well, now the plane's no longer this flat surface. So if I change this angle, say it's at the point of this pencil, so this is horizontal, right, the plane. If I change the angle to here, it's now this sloped surface. But just by thinking about this point where it intersects, as well as the vector coming off of it, the line coming off of it, you can get an idea of what that entire plane looks like, which plane you're talking about, right? Some people are great at visualizing that, some not so much. But the idea is, because I can describe it with just that point on the plane, and then the vector perpendicular to it, that normal vector they call it, I can generate the entire equation for the plane. What that ends up looking like is because in order for that vector to be... Go ahead.
Does it look like a normal vector?
Yeah, a normal vector as well. It's normal is just another word for perpendicular to a plane, but yeah. So if I think of a normal vector, in order for it to be orthogonal with that other is going to have to be equal to 0, sum p to q. Well, if you generalize that out to have x, in other words, I don't know where the terminal point is, but I know where that initial point is on the graph, x1, y1, z1. Simplify things out a little bit, you get this equation. And that's what is called the standard form for equation of a plane. Okay? So again, that's just some point x, y, z, or x1, y1, z1, along with a vector that's perpendicular, that's normal to the plane, ABC. So what you're multiplying is by the vector, kind of like slope. Same thing for the lines. Then you also have general form, which just means get rid of the parentheses. So standard form still is kind of like point slope form. You can kind of think about it comparison-wise. And then the general form is kind of like slope intercept form. Except for the D isn't quite as clear as what the y-intercept is. Okay? So, if I have this, I want to find the general equation of this plane passing through those 3 points. Well, the problem here is, it's kind of hard to figure out the normal vector to just 3 points, right? So what do I need to do? Any ideas? I can't easily find a normal vector to those, but I can find a vector perpendicular to another vector, right? Well, how do I turn those into a vector? Yeah. So in other words, just make P, Q, and R. And then I'm just going to think about, okay, if I had these as going out, somewhere out here, well, P, Q, and R. What's normal to them then, once I have those vectors, I want to find the vector coming out. So if I do this, I'm going to go Q to P, Q to R, and it honestly does not matter which ones you're using for this. It'll work. What's your vector for Q to P? Two what? 2, -3, 2. For Q to R? 0, -8, 1. So how would I find a vector that's perpendicular to both of those? Cross product. Take the cross product of them. So if I cross these two together, how do I cross them together? IJK. You could rewrite them into that linear combination form. Honestly, I don't bother, because I'm just going to write these down as is. So what's going to be the first number then? Coefficient on the I. Heard somebody say it. 13. -3 minus -16 will be 13. What about for the J? 2, except you have to flip that middle value because it's attached to the J. And then for the K? -16. Minus 0 is still -16. So this vector, this is your normal vector. This is perpendicular to the plane. So then to write the equation, what else do I need? One of the points. Does it matter which point? No. So which point do I want to use? Okay, let's use Q. Since we made that our point of intersection, let's use Q. So then when I write this out, these are the things I'm going to multiply by. That vector, that's going to be 13 times x minus the 1, minus 2 times, or plus -2 times, y minus 5, and then -16 times well, just z minus 0. I keep going to the right parentheses for some reason. Equals 0. Now that is which form? Standard. So this is standard form. Can't spell that. Wow, I'm awake. Okay, so that's standard form. How would I find general form? Don't make it harder than it is. Yeah, multiply out, distribute, get rid of the parentheses. So I knew that 13x minus 13 minus 2y plus 10 minus 16z is equal to 0. So I get 13x minus 2y minus 16z, and what? Minus 3 is equal to 0. This would be your general form. And the reason we change it to general form is, if I look at what a different class did earlier on this problem, they didn't choose the same point. They chose the point P instead of the point Q. So they ended up with this for a standard form. But look at the general form. General form, you'll end up with the same thing, no matter which point you're using. So that's why you'll change from that standard form to general form. Okay. Questions so far? We're pretty decent clips. I'm going to actually keep going. Let's see where we get to. Planes in space. Now, if you have two planes that are crossing each other, okay, well, you got a few options. Kind of like lines in two space. Either they're going to intersect once, or what else could you have? If they're parallel, they never intersect at all, or same line where they overlap each other and infinitely many solutions. You can actually have all three of those with a plane too, but when they intersect, they don't intersect in a point, they intersect in what? A line. Now, the trick is, for these, you're going to want to use the angle. I'm going to want to find the angle between these sometimes. Now, this angle here, well, that's kind of a hassle because I don't know what the vectors going on are exactly. I could generate them and figure out that point of intersection just somewhere along that line, then find that angle, or I could cheat a little bit. Okay? Mathematicians usually prefer the easiest way possible. So, what you can actually do is take those normal vectors. This plane here has this normal vector, the first one going off this way. This flat plane down here has it one coming straight up. Well, the angle between these two perpendicular vectors, these two normal vectors, will actually be the same as the angle between the two planes themselves. Everybody see that? Now, the nice thing about the normal vectors, well, if I look back at this equation we just did, the normal vector, I can find real easily from the equation. What is it in the equation? What's the word for those? Coefficients. The 13, negative 2, negative 16 are just your coefficients here. So all I have to do with this is find the angle between the two vectors, and the two vectors are just the coefficients. So if I have... Then, once I have those normal vectors, I can find the angle between two vectors, right? Just use this formula. Or, if they're perpendicular to each other, the dot product will just be 0 when you go to do this. If they're parallel, one's just going to be a multiple of the other. So it's not the same formula we've done before, just apply to normal vectors to these planes rather than just vectors in general. So if I have these two planes, I want to find the angle between them first. What do I do? Well, what do I need in order to be able to do this? The normal vectors. These are in general form as is. They're equal to 0, right? I don't have any weird distribution to deal with. So the normal vectors for this first one here is going to be what? 2, negative 1, 3. And for the second one? Negative 1, 2, and 1. Okay? So those are my two normal vectors. So if I want, first off, are they parallel? No. If they're parallel, there would be some multiplier to take you from n1 to n2. So they're not parallel. So then I just need to use cosine of theta is equal to the dot product, the absolute value of their dot product. Well, what's the dot product going to be? Negative 2 plus negative 2 plus 3, in other words, negative 1, which turns into 1. So I got 1 there. On the bottom, I have the two magnitudes. What are you going to get for the first one? Yeah, 4 plus gives you 14. Underneath here, 1, 4, and 1 gives you 14 times 6 is 84. So then, just inverse cosine. If I do inverse cosine of 1 over the square root of 84, I end up with inverse cosine of that it's inverse cosine of that. Sorry. Degrees. 83.74 approximately. So that would be your angle between the two planes. Now this thing asks you another question that they actually haven't talked about yet. What's the parametric equations of the line of intersection? It's a little bit different way of thinking about it. How do I find the point of intersection of two lines? If I have like 3x minus 2y equals 7 and 4x plus 8y equals 15. You can set them equal to each other and go from that direction if you solve everything, but there's usually an easier way. I would use elimination. You could also do substitution. Any of those would work. But this one, I kind of like elimination because this is already set up for negative x here, right? So if I take the first equation as it is, 2x minus y plus 3z is equal to 0. What would I have to do in order to be able to eliminate the x? Multiply by 2 and add it in. So I'm going to take 2 times that second row. That gives me negative 2x plus 4y is equal to 0. So then, when I add these up, what do I get? 3y plus 5z is equal to 0. Now the problem here is I don't have another equation to work with, right? I just have these two planes. Well, so what I'm going to do then is work with what I have. I'm going to solve this one for y. What do I get when I get y by itself here? Negative 5/3 z. Or negative 5z over 3, however you want to write it. So then the idea is I'm going to use this to get x also in terms of z. So if I plug this back in up here, I have 2x minus this negative 5/3 z is going to turn into plus, and then plus 3 times z. Simplify that out a little bit. What fraction do I have in front of the z? 14/3 z is equal to 0. So just 9/3 plus 5/3. So then what would x be equal to? Well, 2x would be negative 14/3. 14/6, which would be 7 over 3. So now I have x in terms of z, I have y in terms of z, and I have z, right? But for this, what I end up wanting to do with it is I'm going to take just z and set it equal to something that's going to make this stuff work nicely. Now they want parametric, so that means I'm going to have what in here? T. So what number would be nice to make z equal to? Well, 0 is going to eliminate too many things. Just t is going to leave me with these fractions. If I don't want the fractions, I wouldn't just do t, I would do what? 3t. Because if I make z 3t, What's y going to be? Negative 5t. What about x? Negative 7t. This is your parametric equation of that line, where these things intersect. Does that make sense? So they have two different problems going here. They find the angle, and then finding the equation of that line formed when they meet. Questions on either of those things? Okay. One last thing. Well, actually, a couple things. You wouldn't be asked to do this on a test, but it is kind of interesting. If you want to be able to sketch a plane in 3 space, typically what you do is find your points of intersection. You find where it's going to hit the x-axis, where it's going to hit the z-axis, where it's going to hit the y-axis. Draw that triangle and shade it in. That's typically the way they show a plane on there. Because any plane going through there, unless it's flat out parallel to one of those, will be hitting all 3 of those things, right? So that's an easy way to draw it. On a test, you're not going to have to draw a plane, but that's how you would actually draw it. Well, no, they extend forever in each direction, but basically you're drawing just that one portion of it. Okay? And the very last thing, if I want to find the distance between a point and a plane, okay? So I want to figure out how far it is from that, the shortest distance possible from that point to that plane. Well, what I'm going to want to do for this, well, it's actually a projection. Remember when we dealt with projections? Yeah, they look a little bit weird, but honestly, it ends up not being too bad. So that distance d is just the projection of that normal vector onto that line P to Q. So that'd be the same as this over here. So what I can do for this is actually just do the formula that we've had before. Just applied to that normal vector. So it's just the dot product of that P to Q line with the normal vector divided by the magnitude of the normal vector. Sure, its length. So, if I want to find the distance here between this Q and this plane, well, the problem is I need another point that's on this, that's actually on here. What would be a point on the plane? How could you find one easily? Well, I'll give you a vector that's perpendicular to it. But I want a point. In other words, I want some x, y, and z value that would make this statement true. So in other words, I would do it the easiest way possible. Well, 1 and 1, you can do that. Basically, pick 2 values and find the third. I would do 2 zeros. Which things here would you want to make 0? Yeah. X is 0, Y is 0. If that's the case, then Z has to be 2. You can also do 4, 0, 0. Either one's going to work. I wouldn't mess with the 3 just because fractions. So if I do 0, 0, 2, the idea is this is a point on that plane somewhere. What I'm visually doing is drawing a line from P to Q, and then finding the distance with that projection. Formulaically, I need to find a normal vector. Well, what's the normal vector for this plane? Yeah, just those coefficients, 2, negative 3, 4. And then, yeah, it's just these coefficients. That's the normal vector. And then I need the vector P to Q, which is so from P to Q. 2, 3, negative 3. So that's the vector from P to Q. Then I'm going to do that projection. So I'm going to take the dot product of those 2 vectors, which is going to give me what? What plus what plus what? Okay. So that gives me negative 17. On the bottom, I need to take the magnitude of just the vector n. So that's going to be the square root of what?
29.
Yeah, you're going to take each one of those values from n squared, so 4 plus 9 plus 16, which will give you the square root of 29. So, the distance between those two things is 17 over the square root of 29.
Is that okay to read after the mom?
For this, I'll let you do it, yes. If you rationalize it too, that's fine.
Yeah, she looks
No extra credit. Anyway, questions on any of it? Okay, one chapter left to go in the book.